So, yeah, TACC has several machines available for use, and Maverick 2, Frontera, Lone Star 6, Stampede 2. You can go to the TACC websites to see what each of those machines entail in terms of the computing power. In order to actually use TACC, you need an allocation, and to get an allocation, you have to be a faculty member or a principal investigator on a research project, and you basically have to request those allocations. So for you guys as students or later postdocs, whatever, you'll have to request that allocation somehow. Usually for students, that comes through your advisor. So your advisor will request the allocation and add you to it, and then you'll be able to use it. So for me, right here, I only have one allocation. It's on Stampede 2. Stampede 2 is actually going to be decommissioned later this summer. So, this will be one of the last demonstrations on Stampede 2. But there's other computers, and there's computers that will replace it, right? So, and the way you interact with them is pretty much the same across all the compute systems. And TACC has excellent documentation. So, for example, with Stampede 2, where's the one I want to pull up? Yeah, so Stampede 2 has two different types of kind of nodes in it. So it says, right there, the system specifications, it has 4,200 Knights Landing nodes, and each of those nodes have 68 processors. Right? So I don't know how many, 68 times 4,200, that's how many total processors you have available to you. Now, no one uses all that at once, right? Because you just can't get that much of the machine. There's a lot of people submitting jobs all the time. And so, it's unlikely you'll be able to use that much. There's also 1,736 Intel Xeon Skylake nodes, and there's 48 cores on a Skylake node. And you can request which of those you want, whatever. Here's kind of a picture of what it looks like if you go out. So TACC is physically at the Pickle Research Center in North Austin. And if you go and look at it, that machine there that's with that painting on the side of it, those are just racks of a bunch of different nodes, compute nodes that are connected through a high-performance interconnect called InfiniBand. So let's log into TACC, right? Or in fact, specifically, we're going to log into Stampede 2. And so the way we do that is with, we're just going to use the terminal. Stampede doesn't have any kind of graphical user interface at all. The only way we can interact with it is through the terminal, and that's part of the reason why it's the first few weeks of this class we just deal with basic Unix command and how to interact with it, because it's essentially how you interact with any supercomputer. So first thing we're going to do is run SSH. So SSH is a protocol. It's short for Secure Shell, which basically is going to allow us to tunnel in via the internet to interact with TACC. And so my TACC username is JT Foster, and then the machine name Stampede2 at tac.utexas.edu. And this has a two-factor authentication, so I'll have to put in my password first, and then it's going to ask me for a TACC token. And the TACC token, there's actually an app for Apple and Android. It's just called TACC token, and there's a token that updates. And so, I just use this. I'll put in this number, and then I'm logged in. Yeah, now I'm logged in, right? And there's a couple separate file systems within TACC. So you log in to what's called a login node, and it has your home file system. So in my home file system, basically I have Anaconda or Miniconda installed so that I can run Python and have virtual environments and stuff. And then of course I have Julia installed there as well. Your home environment also includes your Bash RC, there and all that, which we've covered in this class. So you can basically install your own profile files into this home directory and modify, all the things that we talked about that you can do in those. Have aliases, modify your path, all that kind of stuff. So there's other file systems. So in your home file system, you can only have, there's a quota, you can only have 10 gigabytes of data in there at any given time and no more than 200,000 files. So, as look at the note over there, it says, the home file system is not intended for parallel or high intensity file operations. Basically, in your home directory, you would keep things like executables that you want. Maybe you compile some code there. But when you actually run code and that code generates results, like you're running a simulation that's outputting to files, you always want to do those in either the work or the scratch directory. So you can see there in the work directory, you have access to up of a terabyte of data and 3 million files. And in the scratch system, there's no quota, meaning you can have as much as you want there, but notice that files are subject to purge if access time is more than 10 days old. So if you have, in Scratch, if you have old files, more than 10 days old, they could purge them, they could delete them. But, for temporary work, say you're compiling a bunch of stuff and it's going to generate, millions of intermediate temporary files that you're going to delete later, you can do that in Scratch, and then once you have the compiled binary, you can move that to another place. Right? And so those you always want to work in the work or Scratch directories, and there's environment variables defined so that you can move to them. So for example, I could go cd work, and then if I print working directory, you can see that's work 2, and then versus if I cd home and print working directory, you see the files home 1, right? And there's also shortcuts, aliases, if you will, defined. So, for example, there's CDS, that's like change directory to Scratch, right? So you see it's a Scratch directory. Right? Also CDW for CD to work, right? Okay. So what I'm gonna do today, we're just gonna do it in the Scratch directory because I don't care if it's purged later. It's just for demonstration today. So there's basically 2 ways. Again, in the login node, this is for your customized settings. This is for building code, developing code possibly, but you don't run code from the login node. You have to request a queue, and there's basically 2 types of queues. One is interactive and one is non-interactive, right? So basically what a queue is it's a line, right? There's, as we showed, there's thousands of processors available there to us, and we want to get a chunk of them to do some parallel work on, right? And we can request an interactive queue with a command called idev, which I'll show you in just a second, or we can submit the job non-interactively. So we submit it, and it goes and sits in the queue until until that allocation of processors is available, and then your job will run, without you even looking at it, interacting with it anyway, and then you're done. So we'll start with the interactive queue. So what we'll do is we'll say idev, and there's a help that basically lists all the different commands. But what I'm going to do is basically ask for one node, and I'll ask for 48 processors. Okay, so it goes through basically I'm pending right now. That job status is pending. That means I'm sitting in the queue waiting for 48 processors to become available, and then it's going to launch me in and allow me to use those processors. So we're almost there. Yeah, and so now I'm actually on one of the compute nodes from where I can launch my job. And what I'm going to do, just for demonstration here, is I wrote a little. Funny enough, I had ChatGPT write this for me. I literally said, ChatGPT, write me a MPI-based C++ Hello World code, and it wrote that, and I copied it and pasted it in there. Of course, I know how to write it myself, but I'm lazy. All coders are actually just lazy, right? It's like we build things that do things for us. So, so here's my parallel Hello World program, and this is written in C++. And so we can compile it. Whenever you compile a code that's going to run with MPI, there's a wrapper on the general like C and C++ compilers in this case. So what I'm going to run is the compile command for MPI C++ on Hello World, and by default it's going to compile that, and the name of the executable that it generates is a.out. I can control that. I could specify an option to output hello instead. And so now if we look at that, then my executable is hello. These two things are the same. This is the default name, and that's when I gave it the name, right? So now we're ready to try to run this, and we can run it. There's a command. It's called ibrun, which is a wrapper on MPI exe execute, and you can specify different arguments. There's a help for it too. It tells you all the different commands, but by default it's going to basically use all of the nodes that are available. And if you remember, I requested 48 processors, right? So if I don't give it any other arguments, if I just say ibrun hello, by default it's going to run on 48 processors because that's what I requested. And then we've all seen how a Hello World program in MPI works. Basically, each processor prints its rank and the size, right? And so what you see there, output to the screen, is the result of that. And of course, we can't control the order in any way, right? So our program ran, and 48 processors printed to the screen, just like that, right? So that's an example of how to run a program using IDEV. So we can also then, I'll demonstrate how to run it using the non-interactive mode. So I have this script here called submit.sh. It's just a little bash shell script, and it's got these sbatch primitives, that special syntax at the top. And in this case, basically that specifies the number of nodes and the total number of tasks that I want, right? So I'm going to run this on the same number of nodes and processors as we did before. It's just this time, and then the command is ibrun, and we can change that to, since I did change the name, we can change this to hello, right? And so then with that, what we're going to do is we're going to submit this to the queue, like I mentioned, and the command for that is sbatch, and then we have some options. So in this case, I want the output of the program to go to a file, and I'll call that file simulation.log. It's just a log file that's going to print out whatever is printed to the screen, right? Or actually store, because this is going to run non-interactively, right? We're not going to see it in any way. And so if we're printing to the screen and we want to be able to see those results, we got to store them in a file. And so that's what that does. You also have to specify the queue. So the queue, in this case, we'll just use normal. There are different types of queues. Do I have? Yeah. So there's development queues and normal queues, and you can see the number of nodes that are available in each of them. There's also, in some cases, what are called large queues. So they have like larger memory, larger amount of RAM on those nodes than the other nodes. So you can look at the documentation to kind of get a better idea of which queue you submit to. But most of the time, and if you don't know otherwise, you can just submit to the normal queue. And then the time that you want to run in minutes. So in this case, we know the Hello World program doesn't even take seconds to run, right? So I'm just going to specify 2 minutes. And the reason, so the maximum is 48 hours. So if you have a simulation that runs longer than 48 hours, you're going to have some type of restart capability, basically, that you can restart it and run it longer. that there is the reason that you wouldn't just choose anything, like even if you know your simulation is only going to take seconds, you want to try to choose. What I'm trying to say is you want to try to choose a time that, of course, is going to allow your simulation to finish, but also not be too large, because your time, that your runtime, your wall clock time that you're requesting, it actually affects how fast you're going to get in to run your job from the queue, right? Because if I'm requesting 48 processors, the queue doesn't know anything about my code. I do, right? And so if I request that I need 48 processors for 48 hours, the queue's going to make a judgment on how long I sit in line versus when I actually get the access to the processor to run it, based on the fact that I'm going to tie up those processors for 48 hours, right? So if I put in 48 hours, I'm going to sit in the queue a long time until enough space is available in the machine for me to be able to run my job. So anyway, put something reasonable down for your queue time. And so and then those are just commands, arguments, and then the script we're going to run submit.sh, right? Again, which has the primitives in there for how many processors to run and whatnot, right? So when I run that, and I'm going to have to be quick because I'm not going to sit in the queue very long if I'm only requesting 2 minutes. So I'm going to run this, and then I'm immediately going to query the queue to see if I can find out what my status is in there. So I'm going to run that, and then I'm going to say SQ -U JT Foster, and there I am, and I caught it just in time that it's actually running, right? So otherwise it would have been status PD pending, so I would have been sitting in the queue. So right now it's actually running the job, and then you can see the output. By this time it's done, and you can see if I look at remember I told it to specify a file, simulation.log, and if we look at what's in simulation.log, it's the output of all those, the Hello World program, right? So ran this, in a completely, non-interactive way, all right? So that's how there's 2 examples for the Hello World program. I thought I would also just go ahead and, show as well, just so I have my solution to project 3 here, and if we go there, well, what I can do is just git clone this, so there's my project 3 solution, and with Julia, what we'll do is launch Julia with in this project and instantiate the project. So there's nothing installed here. So this actually, when you guys open up a code space in class, that's part of what happens in that first few minutes. While it seems like it takes a long time to set up, it's because it's installing all of the project files that you need to complete it, which for this project it's like a lot. I mean, it's grid app distributed, and differential equations and all that stuff. So in this case, what we're going to do is we're going to go, so I cloned the repository locally. I'm going to go into the package manager, type instantiate, which is going to, basically download and build all the files in the project. And while that's building, I'm going to say, when we use MPI from Julia, right, it automatically installs, MPI.jl. It's one of the dependencies of the project, and that automatically installs its own MPI installation, right? But when we use Julia or when we use MPI on TACC, we want to make sure that we're using an MPI version that's compatible with InfiniBand, and that's this MPitch. That's this MPitch. I think I told you when we talked about MPI, right? MPI is just a standard, right? It's like definitions for how to do parallel computing and how the API should work, but there's no specific implementation in the standard, right? And so then the concrete implementations are OpenMPI, MPitch, MVPitch, all these, right? And so, like, if I were to go back, let me get out of Julia for a second. Go back over here and say which MPI EXEC. Oh well, I need to go back onto a compute node. So if I go back onto a compute node, they don't even let you run MPI EXEC unless you're on a compute node. So let's give this a second. Yeah, so let me say which MPI EXEC. You can see that it's pointing to this, op Intel compilers and libraries 2018 to Linux MPI Intel. Right, so that's the version of MPI EXEC that is optimized for Stampede. And so we'd prefer, instead of allowing Julia to install its own version, which is not going to be optimized to work with InfiniBand on TACC, what we really want to do is just use the one that's already there. Use the version of MPI that's already there. And so it turns out there's a tool to kind of help us do that. I'm going to go back, get off the compute node, and go back in here, launch Julia again in this project, and add a new package called MPI Preferences. Let that install. And then what we'll do is we'll run this command right here using MPI preferences. MPI preferences use system binary. And what that will do, we'll find the local MPI version, and it tells us, right? It's this one. It's the one, the Intel MPI library 2018 update 2. That's the one we just looked at, right? So it found that local one, and it changed the preferences to that. Okay. And so now we can actually we'll get out of here again. I'll request. So I'll do idev, just without arguments. The default there is to give us a one node for 30 minutes, which has 48 or 68 processors, depending on which node it is. I think it's the 68 processor, the Nice Landing chip. So then I can go in here and then I can say IB run, number of processors 4, Julia, project, source, project 3. And of course the first time we run it, it has to compile everything and run. So this is my solution to project 3. And we know that when you run project 3 successfully, it generates those VTK files for visualization. So when this runs, and it'll take a few minutes because it has to compile everything the first time, then we'll be able to see those results here shortly. So it's kind of a quick demo. Any questions? And again, since I'm recording this, I'll if everything worked well and you can hear my voice well,
and I'll put that on YouTube and send a link so that for future reference, because I know you're not taking notes, and it'll probably who knows when you want to do this, but at some point you'll want to do this in your research, and hopefully you'll find this video useful.